So, hello everyone. My name is Aman Jagwani, and this is Victor Lazzarini. We are from Maynooth University in Ireland. Very happy to be here. Thank you for having us. So today we are going to talk about again granular synthesis, granular processing for live performance specifically. And we're going to talk about this cross-platform framework for thinking about granular processing in a textural way, specifically for live performance. So the motivation for this is that granular processing allows a very large amount of transformation of audio and has a very wide parameter space. You can control things like grain size, density, pitch, jitter. Like there's a bunch of different sounds that you can get from this one technique, which is very useful in sound design. But sometimes in live performance, having so much control can be maybe distracting from the live performance aspect. And I'm a musician, I'm a drum set player, so very often I like to do live electronics with drum set. So it's sometimes hard to have very complex controls of many different parameters while playing drums as well. So the goal of this framework is to kind of deparameterize granular processing to have very fixed textural identities, or something we're calling recipes, that will have one particular identity of the sound. For example, you can have pitch shifting micro loops, or you can have stuttering audio. Each recipe has one identity, and then you just control them with two macros. We're calling them energy and intensity. So like I can play drums, control two macros, modulate the sound. So that's the goal. And another goal is that this is cross-platform. So it works on desktop environments, microcontrollers, which we'll show you, and also FPGA-based platforms where we implemented also spectral granular synthesis, granular processing with this. Yeah, so we're going to go over this whole thing for you today.
Yeah, I just want you, just before we move on, just to put the context in the time for granular synthesis we're targeting here. We're going back all the way to Gabor and in his formulation of two things, actually. One, which is the actual granular idea, the principles of acoustic quanta, but also he is the father of time frequency analysis. So we feel that particularly the spectral approach is a kind of realization of his idea, both of time frequency analysis and synthesis, and also granular synthesis. So that's where the context and where we come from.
Okay, so I'll go over the framework and how it is organized first. So this framework, basically, it's about creating granular recipes, and each recipe has a textural identity. So we have two roles defined in this, the programmer and the performer. So while programming, we write the recipes, it's basically like a behavioral preset at the developer level to constrain and define like the evolution of the different parameters with each other as they are modulated by the macros in live performance. And so when you're making a recipe, or you're deciding that, okay, I want these stereo spread pitch shifting loops in this texture, that's kind of like a compositional process embedded in the development process. So that's the way of thinking over there. And then the role of the performer is to manipulate the two macros, which they have control over, which is we are calling energy and intensity, and we'll see how we can define what to do with the macros as well. And then also you can have quite large transformation if you actually switch recipes while performing. So you can map it to a MIDI control or a sensor or a switch, and switch the recipes and have like wide transformation of audio. So you can go from smooth loops to stuttering like with one button. So that's also quite a dramatic shift while performing, for example. And there's as I said, not too many controls. So that gives you time to also co-perform with other instruments, or like a modular synth or other systems. So the framework is organized in very simple layers. So at the top is platform-based, very thin bindings to connect the MIDI. So things like MIDI, UIs, sensors, or hardware, the audio input and output from hardware to the framework. Then there's an API to make your recipes. And there's a DSP engine at the bottom as well, which has granular and spectral time domain and spectral granular covered. So this is the recipe API. You basically have to just implement these functions. So in the time domain, there are two different rates at which you can implement modulation. So granular processing, one of the most interesting parts is when things evolve over time. So there's the on sample method, which is basically at the audio rate. So you can decide what kind of evolutions happen at the audio rate on a sample by sample basis. So pitch shifting or modulating the scanning of the buffer, things like that can be quite interesting in that. Then there's on spawn, which is like at the grain by grain level. So at a particular each grain you can modulate where from the buffer you're reading, or the pitch, or um, whatever you want to basically modulate in that. And then you just how you implement the functions for updating the parameters from the energy macro and the intensity macro. The difference in the spectral part of it is that we also have the on hop method, which is on the hops of the short time Fourier transform. So that's a different rate level compared to on block. We'll see more of that later. And then this is a example of how to implement these functions. So the first one basically decides when you change the energy macro, how grain size, density, and jitter transforms. Then the on spawn basically adds pitch shifting or like different pitch, quantized pitch shifting per grain, and also reverse of the reading of the buffer per grain. And then the on sample method basically uses a phaser to kind of scan the buffer and create jitter across where the grains are being read from. And then the important part of this framework is that it's cross-platform. So the same code base runs on a microcontroller. So I'm going to show some examples with the Electrosmith Daisy, which is a STM32 based audio microcontroller platform. It takes care of all audio input, output, sensors, MIDI, all of that is integrated. So it's a good platform for experimentation in the embedded domain. And then the same code can also run on a FPGA platform. So very often FPGAs, which are field programmable gate arrays, they are integrated circuits or chips which have programmable hardware. So when you're programming them, you're actually programming hardware units inside the chip itself, not software. But they are often paired with a ARM CPU, so which communicates with the programmable logic, which is the hardware part. So you can run this recipe system on the CPU and control the processing on the FPGA programmable hardware. We have examples of that as well. And then everything is statically allocated, so that's it's helpful for embedded systems. So the caller manages the memory by just providing the buffers for everything. And then UI to DSP communication is with a single producer, single consumer circular buffer. And you call these set recipe, set macro, and that uses the circular buffer to do the communication.
Yeah, so here we just have an outline of the time domain and spectral domain idea of the versions of the framework. Well, the time domain is, as you usually expect, granular synthesis to be just basically, these granules being picked up from the audio signal and recomposed, which is only a partial representation or partial realization of the acoustic quanta, because you actually have the time dimension, whereas in the spectral domain we have both the time and the spectral or the time frequency realization. So we think of this grid where you across time and across frequency. So there is there's some differences, and in the time domain, of course, you would choose it because it's less demanding, and so on certain computation devices you would expect that to be the most preferred. But the spectral domain is perhaps the most complete realization.
Yeah, so we have some examples of recipes implemented on both for both time and spectral domain. So in the time domain, examples will be on a DAISY, which I mentioned, and the spectral domain will be showcased on a FPGA platform, because spectral domain is higher computational cost. So running on the DAISY is very difficult for that, but FPGA supports it well, as we'll see. So this is a first example of a recipe. So this one is like pitch shifting, overlapping textures. So there is a MIDI controller which will So the left slider is the energy macro, and that changes the length of the grains and the density. And also it creates like a pitch bias. So the higher the energy macro is, the higher pitch is started. And then the right one is the intensity macro, which does feedback and pitch thing as well. That was one example of a recipe. So this is the second one. This is more sparse, and the rate of producing grains is more asynchronous in this. It's more jittered and more percussive textures, and it goes from like a tight mono cluster to wide stereo with intensity, and the speed of grain production is with the energy macro. It's just basically a simple sequence going through the daisy, which has a framework on it. So it's basically, the idea is it's that each recipe has its own different identity of sound texture. And this one is like a stuttering recipe. Tempo sync stutters basically. So the intensity macro on the right, that controls the subdivision of the tempo sync. And the board over there, that's the Daisy board. It's like a development board for the Daisy it's by Electrosphere. Basically, then you don't need to use a breadboard. It lets you prototype very easily.
Source is the same.
Yeah. So now we'll go to the FPGA part of this a bit, and we'll go over the spectral domain granular processing on the FPGA. So just a little bit background about the architecture in FPGA-based boards. So FPGA field programmable gate array, and the programmable hardware is the most interesting part here. So traditionally, FPGAs are programmed with very low-level hardware description languages, which is quite, it's very domain-specific and quite, sometimes it's out of reach for general audio programming, but you can also program FPGAs with C and C++ with HLS tools, which are high-level synthesis tools. So that's what we use. So we use them to make modules that run on the FPGA basically in the programmable logic part. So for the spectral granular, we basically made a series of spectral modules. So they do things like buffer, like a frequency domain delay line. We use the vendor supplied FFT and IFFT modules basically, and then all the windowing, overlap adds, all of that. We made a set of modules that is arranged in like a graph onto the hardware of the FPGA. So the FPGAs are very commonly packaged as a system on chip with the processing system, which is the ARM CPU, and the programmable logic, which is the actual hardware, programmable hardware. And they both have very tight communication and with each other, and managing resources across them is also important. So usually control rate operations on the CPU and audio rate operations on the programmable logic works well. So the way we've divided it for this is we run the recipes on the processing system, and we run the engine, the actual audio processing engine on the programmable logic. And then we use the AXI-Lite protocol to communicate between them. And the board we're using as an example, the Xilinx, is the Digilent Zybo Z720, which has the Xilinx Zinc 7000 FPGA on it. So few examples of recipes on this as well. So this first one is like is a drifting, jitter, and blur texture. So the energy macro controls the jitter of the grains across the spectral delay line. So each grain is basically one FFT frame, and there's a spectral delay line in the with bunch of FFT frames in the programmable logic, and you can jump across them. So, and there's also another example with a drum sample. And then there's blurring, so averaging of frames across the different frames on the intensity macro. So combination of both can get quite interesting sound. That's blurring. Then the spectral buffer that we have implemented also has band-wise 3 bands, and each one has its own independent read pointer, so you can disperse the grain spectrally as well. So this is the second recipe that shows that. You can hear that dispersion more in the drum sample rather than the synth sample in this, but both examples will be shown. And so the energy macro does the randomized dispersion of the spectral grains, and then the intensity macro just does pitch shift in this. So they are randomized 3 bands jumping independently across the spectral bus. 3 bands, which is low, mid, and high. It's quite interesting glitch. That's pitch shift. And then the third one is again like a stutter, tempo sync stutter kind of thing, but since this is spectral granular, the stutter is not as percussive or actually very stuttery. It's more smooth, and it just sounds more like smooth pitch shifting in the tempo synced way. So there's so on the left, on the energy, we have the pitch shifting probability and the bias. So as you go up in the energy, the pitches that jumped across get higher, and on the right is the subdivision on the intensity. You can hear the more tempo sync kind of. So I just give a synth example because the drum it was more effective than the drum one for this example. And then for conclusions.
Yeah, so just as a way of concluding this, the idea of the framework was that we'd like to propose a structured route to do granular synthesis, mostly in performance situations, and that would work across a different set of platforms and applications, effectively. So it's platform agnostic, and it goes from low cost, the DAISY seed, all the way to desktop computers, and including also different types of embedded platforms. It's basically supporting the two paradigms of time domain and frequency domain processing, and so our fully open source software. There's the GitHub there, and then there's some.
So that's the paper
some links
on FPGA based audio processing.
Yeah.
If you want to know more about that, you can see that last link in more details.
If you're interested in the FPGA side of things using high level languages, that's the one.
Yeah. Thank you.
That's all for us.